Okay, let's do 7.2 calculus of parametric curves. So we'll start off with some derivatives and then we'll do some integrals for the parametric equations and those graphs that we were doing in the previous video where it can be defined parametrically, and as time moves on, the x and y both depend upon time. And all of calculus is the next part that we're going to do, which is maybe finding equations of those tangent lines, finding the areas under those regions, finding the length of those regions, all of that stuff. So the first one we'll do is find some derivatives. So if x is dependent upon t and y is dependent upon t, where each of those functions are differentiable on some interval, then dy dx is equal to the y prime of t divided by the x prime of t, where those differentials of dt really will cancel. Okay, so determine dy over dx in terms of t, evaluate it at the given t value, and then let's find the equation of that tangent line and actually sketch that graph. So kind of a whole lot all in this one example 7 here. So first thing I'm going to do is just find the derivative, and the way we do this is dy dx is equal to y prime of t divided by x prime of t, which our y prime in this example is going to be the derivative of 4 minus 8t, which is 0 minus 8. And then I want the derivative of 2 plus 4t, which is 0 plus 4. All that work for negative 2. So the derivative evaluated at time equals 2 is still negative 2. Now, this one was just a constant derivative. Sometimes they're constant, sometimes they're not. If there was still a t left to plug in t equals 2, I would do so. Okay, let's sketch a graph and see what's happening here. So I'm going to eliminate the parameter just like we did in the last video. I have x minus 2 divided by 4 equals t. That was from that first equation. And so then into the second equation, I would have y is equal to 4 minus 8 times x minus 2 divided by 4. I like to simplify that y equals for me. That makes it easier for me to graph it, but of course you're welcome to use your graphing calculator. I got 4 minus 2 times x minus 2, so 4 minus 2x plus 4, so y equals negative 2x plus 4. And then if I were to graph that straight line, which we could see has a y-intercept of 4 and a slope of negative 2. It's also an unrestricted line because I don't have a restricted domain on the parameter t. But you can imagine that at time equals 2, can you see how the tangent line just has a slope of negative 2? Cool, so like this is the curve where I had some object that was traveling along this curve, and then at time equals 2, wherever that is, the slope of that tangent line was negative 2. Okay, let's do the next one. A little bit harder for the next one. Start off with finding the derivative. I have x equals the square root of t, y equals 2t, and I'm going to care about this at time equals 4. So I'll start off with the derivative. dy dx is equal to y prime of t divided by x prime of t for every single parametric equations. So then this is going to become the derivative of 2t is just 2 divided by the derivative of the square root of t. You might think of that as 1/2 t to the negative 1/2 when I did that derivative by bringing the power down and subtracting 1 from the power, or you can think of that as 1 over 2 times the square root of t, which simplifies to be 4 times the square root of t. So now I have still a t involved, which is maybe a little bit more exciting. So dy dx evaluated at time equals 4 is going to be 4 times the square root of 4, which is 8. So the slope of the tangent line at time equals 4 will be 8. Now I do want to draw the graph just like we did before, and this one I'm going to be a little bit more precise on. It has just a little bit more exciting numbers here. So let's graph this. Hopefully we can see from that set of parametric equations. I'll do that off to the side over here so we can see it. X squared is equal to t, so that means y is equal to 2 times x squared. So here is my parabola, but you can see that also x only can be positive because of that square root. Either way, here's the direction of travel. Here's the graph. Cool. So at time equals 4, the ordered pair that I'm at is the square root of 4 comma 2 times 4. So it would be at 2 comma 8. So I'm at the point, I'm going to label it, I'm at the point 2 comma 8. That was the at time equals 4, and you can see the tangent line definitely looks pretty steep. It's got a slope of 8. And we can even find the equation of the tangent line as well. The equation of that tangent line has always been y equals the y1 plus the slope times the x minus x1. That was the college algebra style, the calculus style, same thing, but maybe we called it f prime instead of m for derivative. It doesn't matter, it's still the slope. So my y1 is that y value, which in this case was 8, plus the slope, which happened to also be 8. That's kind of a fluke. And then x minus the x value, which was 2. So that's the equation of that straight line where the y1 was 8, and then the slope was also 8. Cool. All right, so now we've got derivatives, equations of tangent lines. Let's do a little bit more calculus with parametric curves. So here's another example. Find the points on the following parametrically defined curve that have horizontal tangent lines and that have vertical tangent lines. So step 1 is to find the derivative. Anytime you're dealing with horizontal tangent lines or a vertical tangent line, you want to find the derivative. So I'm still going to do that same step 1 of finding the derivative, which is a dy over dx, which is going to be a y prime of t divided by an x prime of t. And so I'm going to do the derivative of each one. Do the y first. So the derivative of t squared plus 18t minus 6 is 2t plus 18. And then the derivative of x is t squared minus 6t minus 2. So its derivative is 2t minus 6. And I suppose I could factor out a 2 on top of each one if I really wanted to simplify that, because there happens to be a 2 in common. And that gives me a t plus 9 divided by a t minus 3. Cool, I have the derivative. Then I'm going to answer the question. And the question is figure out where I have a horizontal tangent line and figure out where I have a vertical tangent line. Let me start with horizontal first. Horizontal tangent line, no matter what the graph is, it doesn't matter. Horizontal tangent line looks like this, has a slope of 0, which means the derivative must be 0. Right, period. That's how that goes, which in this case would be t plus 9 over t minus 3 has to equal 0, which means t plus 9, I set the top equal to 0, which means t is equal to negative 9. So at the time, or t negative 9, the graph of whatever the graph is, I don't even know what the shape of this graph is. I didn't graph it. It's something cool. At time equal negative 9, I'm going to have a horizontal tangent line. But it did ask me to find the actual points. So I need an x comma y. So how do I find the point? The x comma y is going to be plug in negative 9 and then plug in negative 9 to y. So I'm going to have negative 9 into the x first, which is negative 9 squared, minus 6 times negative 9 minus 2, comma, negative 9 squared plus 18 times negative 9 minus 6. I'm going to use my calculator, but I want you to just maybe take a second to realize that that was me plugging in the time value into both the x and the y. Okay, I got 133, comma, negative 87. Ta-da! Okay, then I'm going to do the exact same thing, but for vertical. And so what does it mean to have a vertical tangent line? A vertical tangent line looks like this, because remember, I don't know the shape of this graph. It might look a little something like this. So there is going to be probably some point where the tangent line is vertical. And so when you have a vertical line, that means the slope is undefined, which really just means that all you have to do is take the bottom of your derivative and set it equal to 0. So I went back and I looked at that derivative from before, and I'm just looking at the bottom of my derivative, and that's what I'm setting equal to 0, because that's what's going to give me undefined. So t minus 3 equals 0 means t equals 3, and then again, I need the ordered pair. So I plug in 3 into the x and 3 into the y. So 3 squared minus 6 times 3 minus 2, comma, 3 squared plus 18 times 3 minus 6, and I'll use my calculator. I got negative 11 and 57. So those are going to be the points on this parametrically defined curve that have either that horizontal or vertical tangent line. All right, a couple more things for the calculus. So the next one would be to find the area of a region for the parametrically defined surface or curve, sorry. So what I want to do is just draw a quick graphic, quick example here. Remember that the parametrically defined curve maybe looks something like this, and this could be your x of t comma y of t, where maybe the orientation is kind of defined here as well. The object is moving along that path. If it is non-self-intersecting, if this curve is not self-intersecting, so for example, something that looks like if it overlaps itself, we're not going to be able to find that area. So not yet. So I'm going to leave it as non-self-intersecting. And what I'm going to do is find the area underneath that curve using the parametric equations rather than using the eliminated parameter version like you did in Calc 1. Okay, and so that area is going to be where a and b are now time values. So this is at time equals a and then at time equals b. I'm finding that area. It's going to be the y of t times x prime. If you want to go back to Riemann sums, this was very similar to the height times the width, and then you added up infinitely many. Okay, this is just from Riemann sums. The height would be the y value, the width would be that change in the x, and the change in the x is the x prime. Okay, all right, so now we have the formula. Let's plug and chug. Find the area of the region of this that is above the x-axis and below the following curve, where x is t squared plus 6t plus 3, y is e to the negative t, and t goes from 0 to 1. So we have a formula. We get to plug and chug. So the area is the integral where t goes from 0 to 1 of y times x prime dt. Okay, maybe that was a little bit sloppy. I'll try to write that a little bit nicer. Where the derivative of t squared plus 6t plus 3 is 2t plus 6. That was just do the derivative. Now I'm going to do the integral of e to the negative t times this linear function. This is a product of exponential times linear. You should be thinking of maybe Liate or integration by parts, or better yet, tabular method, where my u was 2t plus 6 and my dv was e to the negative t. And then I do derivatives until I run out, and anti-derivatives to fill in the chart, and then the diagonal multiplication plus minus. That was the nice shortcut for some of these easier integration by parts. This is an integration by parts problem. And I ended up with 2t plus 6 times negative e to the negative t minus 2 times e to the negative t evaluated from 0 to 1. So I'll plug in my bounds, and I ended up with negative 8 e to the negative 1 minus 2 e to the negative 1 minus, if I plugged in 0, I got negative 6 e to the 0, and e to the 0 is 1, minus 2 e to the 0, and e to the 0 is 1. So negative 10 e to the negative 1 plus 8. Ta-da! Okay, let's do some more. So we have the derivative, the slope of the tangent line, the equation of the tangent line. We also have area for these parametric curves. So the last main piece for the calculus would be the arc length of a curve defined parametrically. So the arc length of a curve defined parametrically by x of t comma y of t, where t goes from a to b, is given by the integral from a to b of the square root of x prime squared plus y prime squared. Okay, so you can just memorize that formula if you want, but I think it's way more useful to have at least an idea of where it comes from. So I'm going to think about finding the length between here and here. The easiest way is to break it up as a triangle. So if I'm going to try to find the length of some curve, I'm going to break it up into a bunch of smaller triangles and add them all up. So I'm going to look at one of those triangles to begin with. You can see that the length of that hypotenuse is what I'm looking for. And you can see that I'm going to have a change in x in one direction and a change in y in the other direction. A squared plus b squared equals c squared. So the length is the square root of the other ones squared. And that change in x and change in y is where the derivative is coming from. Okay, that's kind of like a hand wavy proof, but it gives you a good intuition of why that formula works. Okay, but now we have the formula. Let's just plug and chug and see what happens. So here I'm going to say the arc length. I'm looking for the arc length of the curve defined by x equals 1/3 t cubed and y equals 1/2 t squared, where t goes from 1 to 6. So the arc length would be the integral from 1 to 6 of the square root of the derivative of x squared plus the derivative of y squared, both underneath that square root dt. So the derivative of 1/3 t cubed is t squared. The derivative of 1/2 t squared is t. And then we simplify. So then I have the integral from 1 to 6 of the square root of t to the 4th plus t squared dt, which I can simplify even farther as the integral from 1 to 6 of the square root of t squared times t squared plus 1. I just factored out a t squared, but now that I factored out, I now have a product, so the square root can go to each one of those, and that will become the integral from 1 to 6. The square root of t squared is just t, because everything is positive, and then the square root of t squared plus 1. And then I can do now everything, the inside is a polynomial of one higher power than the outside, so I can do a u sub. So I will let u equal t squared plus 1. So du is 2t dt. So du divided by 2 is t dt. I'll highlight that so you can see it, that this t dt can now turn into the du divided by 2. Which is nice because then this will turn into a square root of u times du divided by 2, which is, of course, the same thing as 1/2 u to the 1/2 du. But just like every other u sub you've been doing, is every time I change the bounds, I need to, every time I change the variable, I need to change the bounds. So my old bounds were 1 and 6. If I plug in 1 into that u equals 1 squared plus 1 is 2. If I plug in 6 into that u equals 6 squared plus 1 is 37. So my new bounds are from 2 to 37. And then we're almost there. So then that's going to become 1/2, add 1 to the power, and I'm going to get 3/2 divide by the new power, evaluated from 2 to 37. That was a typo. There it is. And then I simplify, and this is going to become 1/3. The 2's canceled. Times 37 to the 3/2 minus 1/3 times 2 to the 3/2. Ta-da! All right, that's it for the calculus of parametric equations. Thanks.